Okay, let's look at some examples here. The first example in Bernoulli energy equation is pretty straightforward, but there are some points here. We have a siphon. We have a siphon here, and the point here is that the water is drained from a large reservoir. This is a reservoir. Imagine this is a very big reservoir, and by using a siphon, which is a very common hydraulic structures, so we are going to just drain or abstract or withdraw the water from the reservoir or from the lake. So the end of the pipe of the reservoir basically is 3.2 meters below the water level of the reservoir. Okay, so the exit point is 3.2 meters below the surface reservoir. Just imagine this example could be very, very simple example of a real world situations, and you might just end up with this kind of like the cases in reality that you want to just take water from the like the lake, from the river, and this kind of like the structure is very popular. So the exit point is 3.2 meters below the water surface of the tank, reservoir, whatever like that we have in here. And the highest part of the siphon in here, for example, are 2.3 meters above the water surface. The water has got the pipe has got a diameter of the 200 millimeters, 20 centimeters, is like a moderate size, and it discharges to the atmosphere. So this discharge to the atmosphere here, this point. So imagine all of these points, we don't have it. So P2 and P1, we don't have it. Forget about that one. And assuming that the water level at the reservoir remains constant, so the water, imagine it is constant while the reservoir is very big, this assumption is quite true. And that there are no energy head loss. So imagine there is no energy head loss here, for example, for just abstraction. In reality, is not the case, but let's see in this chapter, it is the case. But in the next chapter, you will learn how to calculate energy head loss easily. So the question here is to calculate discharge through the siphon and the pressure head at the crest. Pressure head at the crest here, P3, for example. Crest is like the highest point or highest part of any kind of like a hydraulic structure or any structure is called crest. Okay, the pressure at this point, and they calculate the discharge in here. Okay, so this is the question here. So the way that we're just going to calculate this one is that first of all, we need to just write the Bernoulli equation. And before going to do that one, we have like the all two terms of the velocity and the pressure at point 1, for example, here, point 2 exit point, and point 3 the toughest point. Just bear in mind the point 1, you can choose point 1 exactly at the entrance inside the pipe or outside the pipe. Just bear in mind all of them can be possible. But intentionally, one will have a like the uptaking or like the water extraction from like the tank or reservoir like that, just use like a water surface as like the point 1. It's absolutely fine. So you can see what's the benefit of taking these points as well. So you can see here, because the velocity of like changing the volume, because the reservoir is really big, we can say the velocity is 0. Okay, imagine for the like the Bernoulli equation, we have 3 parameters, Z, V, and P. So one term is excellent, is 0, and the pressure, because it's like the pressure at the water surface level, there is no pressure of the water, so the pressure is also 0. That's really great. So so 2 terms out of 3 is 0, and the third term we know the elevation exactly, so that's like clear as well. So imagine that we're just going to use the reference or datum line exactly here at point passing point 2. So the for example, in that case, you can see the velocity is the question that we want to just calculate, but the pressure is 0. Why? Because this is like the atmospheric pressure, exactly 1 point outside the point, exactly 1 epsilon outside this pipe. The pressure is 0 because it's subject to the atmospheric pressure. So with that assumption, we can easily say like a P2 is 0, but V2 we have no idea about the V2. And here the V3 at 0.3, V3 and P3 is also the question here. Just bear in mind, V2 and V3, if the diameter is the same, so you can, based on the continuity equation, says that V2 and V3 is exactly the same. So anyway, so for any 2 points, we can just write for any 2 points because the elevation height is clear for all points. So for this point, point 1, 2 terms is 0, point 3, 2 terms is unknown, or point 2, 1 point is unknown. So obviously, if you're just gonna write the Bernoulli equation between point 1 and 2, the only like the things term that we don't have it is a V2. So this is what we're just going to write. So exactly, we're just going to write between point 1 and point 2. For point 1, we have 3 terms, Z1, V1 squared over 2G, P1 over rho G is equal to Z2 plus V2 squared over 2G plus P2 over rho G. So for the, on the left-hand side, V1 and P1 is 0, okay? Z1, the reference line, is considered as a like the line passing through the like a point 2. So in that case, Z1 is a 3.2 on the left-hand side. So Z2 on the right-hand side, look here, Z2 on the right-hand side is like a 0. So this is exactly what we just have. So Z2 is 0. And the only terms that is unknown is like this velocity head, V2 over 2G. And if you arrange this formula, V2 is equal to 2G times 3.2 all raised to the power 1 second, so or a square root of this point, or this calculation is a 7.9 meters per second. These are relatively high speed actually. So if you want to just calculate the V3, because the diameter is the same, by using the continued equation, you can just use, say, V2 and V3 is the same, but by using the continued equation, Q is like equal to A to V2 or A through V3, because the diameter is the same, velocity is also the same. We can just write area, or the area, cross-sectional area is like the pi d squared, 0.2 squared over 4. Imagine, remember, for the diameter, pi d squared over 4. This is the formula for to calculate the area. I hope it's clear for everybody. And as a result, A can be calculated 0.0314 square meters. So this is like the area, either A2 or A3 are the same. Velocity, as I said, like the V2 and V3 is the same. So V3 can be easily the same as the V2. We can write 7.924 meters per second. And obviously the discharge, or the flow discharge, is equal to AI. A is like the 0.0314 times velocity, 7.924, and the result is like a 0.249 cubic meters per second. So the second part of the question is asking about the pressure at point 3. So if you're just going to calculate pressure at point 3, is obviously, if you're just going to write the Bernoulli between point 1 and point 3, we can easily calculate, because velocity V3 has already been calculated. The only parameter is like a P3. So you're just going to write the formula between point 1, Z1 plus V1 squared over 2G plus P1 over rho G is equal to P3, Z3 plus V3 squared over 2G plus P3 over rho G. So we know that like the Z1, so we can just keep the same reference. So we can just say, or we can just take the datum and passing through the like the point 1, you can say like the Z1 is 0. Okay, so like the datum level for this calculation is changed. That's absolutely fine. So for any point, it's completely fine, as long as the you just use the same reference line for the 2 points that you're just going to discuss, is absolutely fine. You're just going to change that one. So the Z1 is 0 and Z3 is 2.3 meters. So by substituting these values on the formula for the Bernoulli equation, Z1 is 0, V1 is 0, we know P1 is 0. All of the 3 terms on the left-hand side is 0. On the right-hand side, like if you have like a 2.3 meters here, velocity is, we calculated before in the previous example, 7.924 squared over 2G plus P3 over rho G. So the only unknown parameters is P3. So you're just going to calculate that when we rearrange this formula, and the result is negative. It is like the 2.3 minus 3.2, and the result is 5.5 meters of water. So just bear in mind, this is like the 5.5 meters of water. If we're just going to calculate this kind of like the pressure, not in the meters of the water, or not in the meters of the liquid, if you are told to calculate what is the pressure in newtons per square meter, easily you can calculate, you can multiply this value by the area, cross-sectional area, and you can just see what is that. So this is the example one.